Come to an example on radiation. We have here a glass beaker. The glass beaker is at an initial temperature of 80 Celsius. The mass of the glass beaker is 400 grams, and it has water in there, and the water's mass is 300 grams. And then we have here the height of the glass beaker is 6 centimeters. The diameter of the glass beaker is 8 centimeters. The room temperature is 25 Celsius. The emissivity of glass is 0.92, then the emissivity of water is 0.995. So first I would like to know what is the initial power radiated by the glass to the surrounding, and what is the initial power radiated by the water to the surrounding. And then eventually I would also like to calculate how much time it will take for the glass to go all the way down to 26 Celsius, right? Actually, it ends up that to go all the way down to room temperature takes almost infinite amount of time, because what actually ends up happening is the room temperature slightly goes up and the glass's temperature goes down, and they meet somewhere like a little bit over 25, right? So we can calculate how much time it will take the glass and the water to go all the way down to 26 Celsius, okay, and get an answer for that. So the water mainly radiates through its upper surface. Since the sides and the bottom are in contact with the glass prevents the radiation of the water through the sides and the bottom, and so the area is mainly the top area. So then we're going to take the pi times the radius of the glass beaker is 4 centimeters. So pi times 0.04 squared. So we're converting the 4 centimeters to meters, and then we're doing pi r squared, right? Then we're going to multiply that by the emissivity, which is 0.995. Then we're going to multiply that by the sigma, which is 5.6696 times 10 to the minus 8. And then the temperature of the water is, since it was 80 Celsius, add 273 to that, you get 353 to the power 4. And the power of the water, when you calculate all of that, you get 4.4 watts. Okay? So then let's calculate the power radiated by the glass. Power radiated by the glass radiates through the sides, right, and through the bottom, right? So the surface area of the sides is equal to 2 pi r h plus the bottom is equal to pi r squared. Right? Then we multiply that by the emissivity of the glass, which is 0.92, and then the temperature of the glass to the power 4. So then we have here 2 pi times the radius, which is 0.04, times the height, which is 0.06, right? So that gives you the surface area of the sides, and then we add to that the surface area of the bottom of the glass, which is pi times 0.04 squared. Okay, then we multiply that by 0.92, the emissivity of glass, and then the temperature of the glass is also 353 to the power 4, and then when we calculate that, we get 16.28 watts. So since the surface area of the glass is larger, the emissivity of the glass is not that much smaller than the emissivity of water, right? Slightly smaller, but they have the same temperature, so the glass is radiating more simply due to its larger surface area, 16.28 watts. So just from that, we can kind of see that the glass is probably going to reach the room temperature quicker than the water is going to reach, right? So now how do we calculate the time that it takes for the glass to go all the way down to, let's say, 26 Celsius, 1 degree Celsius larger than the room temperature, right? So how do we do that? Okay, times the rate of change of the temperature of the glass, dT over T. So I'm using the equation for heat transfer and specific heat. The mass of the glass, the specific heat of the glass, and the rate of change, dT over the T. The reason it's negative is because the glass is radiating out heat and it's going to be losing temperature. So its change in temperature, dT, is going to be negative, and that negative will cancel, give you a positive answer here, and this is the power radiated by the glass, right? So then we have here 1.0487 times 10 to the negative 9, T to the 4th minus 298 to the 4th. Then we put the mass of the glass, 400. And we're going to put the specific heat of the glass. So this one is in units of grams. And then the specific heat of the glass is 0.837 joules per gram Celsius, right? And then the gram will cancel. So this is 0.837 joules. You have to use the joule version here. You can't use the calories because this unit is in watts per second, right? This is the power radiated by the glass. So it's watts per second. So that side has to be joules. And then we multiply that by the change in temperature over the time. Then we can cross multiply here, and then we get here 1.0487 times 10 to the negative 9, and then we have dt, and then that's equal to negative, and then 400 times 0.837 gives you 400 times 0.837 gives you negative 334.8, right? dt over t to the fourth minus 298 to the power 4. Then we integrate this. Okay, we integrate this from the initial temperature. The initial temperature was 353 Kelvin, and we want to know how much time it takes to reach all the way down to 26 Celsius, which is 1 degree above the room temperature, right? So the final temperature is 299. And now this one, when you integrate it, just gives you 1.0487 times 10 to the negative 9 T. And then this one gives you, this one we can just change the limits of the integral, the right positive, and then change this to 299. And then we integrate this to 353. Okay, when you integrate that, let's see what you get. You're going to get, this 334.8 is outside here, and then when you integrate that, you get 3.5478 times 10 to the negative 8. And then from there, we can just calculate the time quickly, right? Down to room temperature pretty quickly, right? About 3 hours. What actually will happen, the room temperature will also slightly go up, so they'll meet somewhere in the middle, maybe 25.5 Celsius, maybe 26 Celsius. It depends how big the room is and the specific heat capacity of the room, okay? So we're assuming for now that the room's temperature is not changing at all, so it's staying at 25, and this is the time that it would take the glass to go all the way down to room temperature, about 3 hours, right? How does the answer change for the water? Well, for the water, what will change? Okay, so we put here the area of the water times the emissivity of the water times sigma t to the fourth, and then we put here mass of the water and then the specific heat of the water. Okay, so the area of the water is pi times its radius squared, and then the specific heat of water 4.184 joules per gram Celsius dt over dt, right? Again, the gram will cancel the gram, and then this side has to be joules so that it makes it work out, right? And then we need the sigma here also, 5.6696 times 10 to the negative 8 power. Okay, when you multiply all of that out, you get, so then you cross multiply again, so you get 2.8356 times 10 to the negative 10th dt. Okay, then you get 1255.2. Then you do the same integral. You see here that the glass took 3 hours to go all the way down to room temperature. The water took 43 hours, right? Well, there's two reasons that's affecting this. The water surface area through which it's losing heat is less, right? So it's not losing as much heat as the glass. And plus the specific heat of the water is a lot larger. Since its area is less and its specific heat is higher, it takes 43 hours for the water's temperature to go all the way down to room temperature, but the glass takes only 3 hours, right? So this is a very interesting problem that shows how this heat radiation occurs. And you can see that the water doesn't lose heat as fast, and it takes it 43 hours to reach room temperature, but the glass reaches room temperature in 3 hours, okay? Thank you very much.